So let's talk a little bit about the lattice gauge theory in 2 dimensions first. So imagine that our 2-dimensional universe has some general orientable shape. So you can think of time going in this direction. So you have a moment of creation. So then the universe grows.
Where's the lattice in this picture?
Not yet. So I will start drawing it. So let me start drawing the lattice. So I will cut this space-time into pieces.
This is the Euclidean. This is Lorentzian or singularities all over the place.
There are singularities. So good question. So if we do it in Lorentzian signature, then there are singularities all over the place. Not all over the place, but there are a few singularities when the universe is born, when it dies, and when it splits or joins. So, and currently we don't know what to do with singularities, so we take a simple approach. We just do weak rotation, and so let's call this imaginary time, imaginary space. So this whole thing is Riemannian metric, so locally Euclidean. And then you can, split it into pieces. And it's convenient to split, to make pieces little triangles, but you don't have to. Okay, at some point I will get tired of drawing this. So a bunch of triangles. Okay, I got tired, so also other polygons. My point is that in the end it will not matter. So any way of discretizing the surface, discretizing meaning that we replace, so we draw a bunch of points which are connected by lines, and then we make sure that they're small enough so locally you can think of the 2-dimensional faces as flat. So the whole information about the geometry is, if you like, we could assign some lengths, some angles to the way we connect things. But depending on what kind of theory you want to study on this space, maybe none of that information is really necessary. And so the gauge theory, among other possible theories, is actually kind of the simplest one in that respect, that the only information it requires is not really actually even the metric, but it's the area. So usually, so the metric, of course. So the metric in 2 dimensions has, the metric tensor has 3 components, and it defines the area to form. And so the area knows about the determinant of this 2x2 matrix. So there are many metrics which lead to the same area. And so in this picture, the area is just the area of this piece. This is piece 1, this is piece 2, this is piece 3. And the metric knows about other things, like what are the angles between them, how many triangles, or how many edges meet at the vertex, and so on and so forth. So, so knowing the metric is a much more detailed thing than knowing just the area. Now, as I said yesterday, so if I had metric, the full metric, then so it's being locally flat, you can show that the fact that the two-dimensional pieces meet at the edges at some angles, that actually does not create curvature, so the whole curvature is concentrated at the vertices. But that's beyond the immediate interest of our discussion. So that's
but you're assuming at some point that it's only dependent on like two-dimensional angles.
Yes. Right. That's why I'm stressing it. But why area? So let's just discuss this. So let's look at the plaquette. One plaquette. And so in lattice gauge theory, we have, so the edges come with some orientations. We just choose them. We just have to fix them once and for all. If I choose different orientations, there is a way to recalculate the whole thing, but we need to choose it because we want to assign in a meaningful way a group element to each edge. So this is my edge 1, 2, 3, 4. And so then I want to define a holonomy around the plaquette. This is plaquette P. And the holonomy depends on the point where I start. So let me start at, let's say, at this vertex V. So the holonomy which starts at V is the ordered product of these group elements respecting the orientation, meaning that, so if I go counterclockwise, so I start with G1, so this is right in the Hebrew way, so G1, then we apply G2, then my arrow goes the other way, so I invert G3, then I continue with G4, G5, G6 inverse all the way, and then I came to GK. Okay, so lattice gauge theory is really just a statistical mechanics of well, okay, the version which I'm telling you about now. So there is a version which is Lorentzian, which will not work nicely for generic spacetimes, but we can discuss it. Statistical model where random variables are these collections of, so these are functions from the set of edges to the group. And the Boltzmann weight, so how we measure, how we weight these configurations, has two features. So it's defined in terms of monodromies, but it has to be gauge invariant. So Boltzmann weight meaning that so this is the space of lattice gauge fields, and it is invariant under the action of the group. So this is the space of vertices. So these are lattice gauge transformations, and so they act on these guys. So this is the mathematical notation by sending the group element assigned to the edge. We multiply it. So again, we do it in the Hebrew way. So we take the group element from this group. Corresponding to the source of the edge, so this is why I need this orientation. So the edge connects two vertices, has a source and a target, and so each vertex has a group element from the gauge transformation attached to it. So I can transform this in this way. And the monodromy itself is not invariant. So the monodromy will transform by conjugation. So my Boltzmann weight should be built out of monodromies in the way which is so using the functions which are invariant under conjugation. And what are these functions? So the functions on the group which are invariant under these transformations. These are called the characters. So these are also class functions. So these are and so there are several meanings to this word character, but I mean, one which is kind of simplest is just that if you have a representation of the group, for example, if you have a vector representation, so it means that for each element of the group you can assign a matrix acting in some vector space R. So this is the assignment. Then the function chi R of G, which is a trace in this representation of T of G, would be conjugation invariant. And essentially all such functions, all functions which are invariant, can be decomposed as sums of such traces over all irreducible representations of the group. This is called Fourier analysis. Now, what kind of function should we use? I mean, there are many functions, so in principle, the most general to the gauge theory would use the most general character. So it's it's a sum over all reducible representations. Some function, some coefficient, which just some coefficients times the character. So this would be a collection of coupling constants of the theory. But so the Boltzmann weight would be the product over all. The product over all plaquettes. The function which may depend on the parameters. So depending on the plaquette of the monodromy around this plaquette, computed starting at some vertex. It doesn't matter at which vertex because, as we discussed, the monodromy change of, oh, sorry, I did not discuss that. So if I compute the holonomy around starting at a different vertex, for example, here, then instead of G1 being on the right, it will go to the left. So it is conjugate. And so it doesn't matter at which vertex I start, because this function is gauge invariant. Okay, but there are, among all possible functions, there are some which are kind of nicer than others. And so let me... Let's see in what sense they are nice and what can we expect. So first of all, somehow this information, this function fp should know about the size of this plaquette, because we expect, so we want this lattice gauge theory to, if we want the lattice gauge theory to approach continuous theory, we want, so we want this measure, we want this Boltzmann weight approach exponential minus integral over the Riemann surface, which this triangulation represents, of trace f G f, where this would be the curvature of the continuous H field with some coupling constant. And so if you compute this quantity in 2 dimensions, so this is G m n, G m prime, m prime, and trace, so here trace really stands for the Killing form on the Lie algebra. So, but the point is that if you take into account the fact that these are antisymmetric, f is an antisymmetric tensor, it's proportional to the epsilon tensor. In 2 dimensions, then this whole thing will combine into the determinant. So this will be the inverse determinant of the metric, or determinant of the inverse metric. And so this whole thing, so this the Lagrangian density is essentially 1 over square root of g trace f squared. So it only knows about the square root of g, doesn't know about the finer details of the metric. Or I can write it in slightly Cavalier form. So let me define a 2 form, which is just that. So x1. So this is the symplectic 2 form on sigma. It's a volume form, but because the metric is non-degenerate, it never vanishes. So it's a non-degenerate closed 2 form. Hence, it's a symplectic form. And so if I divide my curvature 2 form by this 2 form omega, I get a scalar. I can square it and multiply by omega. So this is the same thing as my action. So the point is that for this, so I can write this exponential of this, so exponential of minus this. This is approximately, so if I write sigma as a union of plaquettes, so then this becomes a sum over plaquettes of something like the area of the plaquette times trace fp squared, called phi. So f pi is something like the average. Well, it's a rescaled curvature. So if my monodromy around the plaquette is small, small means it's close to 1. So it can be approximated as exponential of the area of the plaquette times some Lie algebra element. Then this is what so this is the expected asymptotics of my Boltzmann weight. So it's exponential of it. So the action is the sum over contributions over individual pieces. So the Boltzmann weight, which is exponential of the action, or the energy in Euclidean notation, will be the product over the plaquettes of things which look like that. As long as I can find a function fp such that it forces the holonomy to be close to 1, and yes.
Can I ask you a story related to history? So we have in the audience a person who looked at this problem in flat space and showed that actually the product of the plaquettes become one plaquette.
Exactly.
And it becomes a one plaquette model.
That's
okay.
What I'm going to explain.
But here, because of the metric is not the same at every place. That's what doesn't allow you to decouple
So I'm going to explain that. So thank you. So this is what. So the nice. Okay, there are many ways of thinking about it, but one statement is the following: that since the metric itself didn't enter my Lagrangian, only the symplectic form. So the theory depends, but at least the classical action of the theory depends on the topology of my Riemann surface and of the symplectic structure. But in 2 dimensions, there is a remarkable result due to Moser, which says that actually the only invariant the symplectic form has in 2 dimensions is the total area. So we know the symplectic form locally has no invariance. Locally, you can always choose coordinates where it has the Darboux form. But globally, you cannot always do that because the integral of the symplectic form is fixed. But you could imagine that maybe there are some local invariants, maybe there are some areas of some important pieces of Riemann surface. Moser says none, there are none. And so the theory is essentially topological, because in addition to topology, it only depends on one number. And since it's topological, you might expect that somehow, if you define it at small distances, it should be almost equivalent to defining it at large distances. So that's the challenge for this Boltzmann weight. So let's see how it goes. So the question which we are going to ask is, how does this theory behave under the refinement or the reverse process of making kind of a more coarse triangulation? So refinement means that I introduce extra edges, and the inverse process is removing edges. So let me introduce an extra edge. So then, let's see. So this is kind of the inverse RG flow. Minor triangulation. So I have 2 plaquettes. Let's call them P1 and P2. And they share an edge. And so let's suppose it was oriented this way. And so the interesting part of the Boltzmann weight concerns these two plaquettes, and the group element which belongs to this common edge only enters the weight of these 2 things. This is the feature of the smoothness of the surface. If, for example, we were in higher dimensions, or we were talking about the Riemann surface defects, which we'll be talking later, you might have, an additional triangle coming at this edge, and so then things will become much more complicated. But in 2 dimensions, life is simple. So this is my group element, which I'm going to integrate over, and I have a function group on, so some G-invariant function fp1 of the holonomy. Okay, let me call this vertex v1, and this actually this is the source of v. This is the target. So the holonomy around the plaquette P1, which starts at the source of the edge E, is a product of some group element. Let me call it M1, so which is a product of all group elements which I have here. Let me just times so it's M1 times GE inverse. So this is GE inverse M1. And then for the plaquette number 2, the holonomy which starts, so the holonomy which starts at the same vertex but is computed around the plaquette 2 is going to be GE times the product of these group elements, which I will denote by M2. So this is M2 GE. Okay, so a nice theory would be such that this integral, so it's integral over one copy of the group, so in general, so it will produce some function, of course, of M1 and M2, which clearly is invariant So it's some function of, first of all, of these two plaquettes of M1 and M2, but this function is invariant under the right multiplication of M2 by something, and left multiplication of M1 by the inverse of that something, because it will be equivalent to just shifting the argument of the integration. This is the Haar measure, so that's the important thing. So it's invariant under the left and right multiplications of the group elements. So f of M1 H inverse M2 H is equal to f of M1 and 2. Therefore, it's just some function of the product of M1 times M2, sorry, M2 times M1, forgetting my Hebrew, 1, which I can forget, so it's just some function, we call it function phi of the product. So there is, so it looks like, so I got again some function on the group, and this function now is evaluated on the monogamy of the combined plaquettes. So this is really the monogamy of the plaquettes P1 combined with P2 without the HE. And we can also show that this sorry. Now remember that the functions fp1 and fp2 were conjugation invariant, and so it means that if I conjugate this guy, meaning that I transform m1, m2 to something like k inverse k, which I can also do in steps. Then put it here, and so on and so forth. So this function phi is also conjugation invariant. So we produced the new Boltzmann weight by starting with two characters, generic characters. We perform some operation. Now, if you think about what this operation is, this is, well, it's called convolution. So phi, P1, P2, P1. This is started a different way. So it's in the sense of Fourier analysis. This is convolution. It's an operation which you typically have when you discuss functions on groups, or functions on spaces with some operations. Now, sometimes this convolution can be integrated to kind of a time flow, group evolution. And so that would be the class of functions which depend on one parameter, the parameter being the area of the plaquette, which have a property that under the convolution these parameters add. So that's the kind of the canonical example of the two-dimensional lattice gauge theory, but it's not the only example. So that was my point. So when Fp of G is, so it's the heat kernel. This is the heat kernel for the time which is given by the area of P on the group. And I will explain now what it is between the unit element and the group element G. So what is the heat kernel? So why is it an interesting choice? Is that the heat kernel can be composed, and so such functions will have a property that f of P1 convoluted with f of P2 will be precisely f of P1 union with P2, where the areas simply add. And this is the property of the heat kernel, which is the so the heat kernel is the amplitude so this is the amplitude for a free particle moving on the group G with the canonical metric. So there is a metric trace G inverse G squared to propagate from 1 to G in time. So this is T. And so the amplitudes compose. So if I propagate from 1 to G. Okay, so now let's unpack this. So if I go from 1 to G and multiply it, so G being multiplied by n, n2. And then I want to multiply it by the amplitude of propagating from 1 to G inverse M1. So this is time T2, this is time T1. These are the areas of the corresponding plaquettes. Okay, so it doesn't tell you much unless I use the fact that this amplitude of propagation is really invariant under the symmetries of the group. So I can equally, for example, I can make the first point, I can multiply it on the left by G. So multiply, so again, making the propagation from the point G to M1. And here I can multiply by M2 inverse. So it will be a propagation from the point M2 inverse to the point G in time T2 and then in time T1. So now, but now I'm propagating from, so I'm ending here at the point G and I'm starting with further propagation at the point G. So since I'm integrating over G, it means that I don't impose any condition at the midpoint. So this is equal to the amplitude of propagation in time T1 plus T2 from M2 inverse to M1.
Wait, what does the trace G minus 1 represent?
So this is the metric. So this is it's the metric on G. And when I talk about the free propagation, think about solving the Schrödinger equation for the, so the wave function would be the, so it would be the amplitude so it will be a function on the group. It describes the wave function of this free particle, and it solves the equation in Laplacian computed relative to the metric which I defined here, d by dt applied to psi. In fact, that's so. It's a solution of. It's a solution of this equation with the initial condition k0 equals delta function supported at 1. Okay. But I just wanted to explain pictorially what does this convolution equation mean with functions. What does this equation mean?
That's a unique example.
Of this additivity? No, it's not the unique example. It's not unique. It's not unique.
What's another?
So so in order to understand what are the options here, we need to do Fourier decomposition. So I need to write for you a formula for this heat kernel.
That's straightforward.
It's straightforward, but let's do that. Okay. So okay, so let me just maybe we'll do it at the tutorial, but let me just write the formula. So the amplitude from 1 to G is the sum over all irreducible representations, the dimension of the representation, the character in this representation, and then exponential of minus t, the second Casimir in this representation. So this is so if you have generators CA of your Lie algebra, so these are generators so then you can normalize them to so that trace in some, let's say, adjoint representation. And then in the representation R, the corresponding sum will be a number, which is the second Casimir, times the unit operator. So it's an eigenvalue of the quadratic function on the Lie algebra, and that's the eigenvalue of Laplacian actually. So so you know this. I mean, you know this formula for at least in the case when the group is U1. So that just show you what it is. So when G is U1, its representations are labeled by integers. So my group elements, so the group element is just, it's a phase, and the corresponding character is e to the I n theta. So this is for the representation which corresponds to an integer n. All these representations are one-dimensional, and the quadratic Casimir is n squared. So in this case, this will become essentially this thing, so which can be Poisson resummed and give you an idea of what this heat kernel is. It's okay. I may make a mistake of some factors like pi up to factor pi e to the minus theta minus m squared over t. So the point is that when t is small, it approaches the delta function at theta equals one of the integers for which the corresponding group element is just 1. Sorry, maybe 2 pi here, so it's 2 pi. Right. So,
sorry for
yes.
the mathematician's question. If the group is finite, then the head kernel is just the delta function at the origin, right?
So if the group is finite, very good question. You can still, I mean, you cannot, you lose this kind of continuous interpretation of amplitude of heat kernel in the group, but you still can make sense of this function.
But won't it all just be the delta, like one at the identity at one?
No, one at identity is this thing. But you can still insert, there is a notion of Casimirs, even for fine groups. For example, for the, in fact, okay, so let's do it for SUN. So you can, so the point is that you can deform the delta function at the unit element by inserting some coefficients here, which depend on the use of representation, but they don't have to be all equal. This is not delta function at unit element. So think of the think of the symmetric group, for example. Then so G is a symmetric group. The useful representations are the partitions of n, and so you can use for this function. It will not have a meaning of the Casimir or the argument of Laplacian, but you can still so you can define C2 of lambda to be, for example, when lambda i's are the parts of the partition and L of lambda is its length. So I mean, it's the nice thing about this formula is that it essentially it captures the large n asymptotics of the corresponding quadratic Casimir for SUN. So this is using sure while duality. That was in fact the starting point for Gross-Taylor approach to the diffuse, relating it to some kind of string theory. Yes?
It seems that it's not unique because you can add class function potential to the Schrödinger equation.
Yeah, of course, you could.
Still, it will be, you have the same.
Not quite, not quite. That will not be, because I used here a lot the invariance under the shifts on the group. So your potential will single out some conjugacy class. So that will not be the case. But what you can do, you can use instead of the Laplacian, you can use other invariant differential operators. You can use higher Casimirs, and that would indeed have this property. So the more general functions, would be functions of that form. The functions which have this obvious additivity property. So this whole thing times the area of the plaquette. So the area will add up, but these couplings will just carry on. So these couplings generalize the Yang-Mills coupling, which I forgot about. Function, there's always letter G. So here I just absorb the Yang-Mills coupling into the area. So these are more general. So this is a generalization.
So Nikita, this can also be understood from the dimensional argument, since it's supposed to be proportional to d squared, the coupling constant, it must be multiplied by something of the dimension of area now. So
yes. So, but and these generalizations are so, but they would correspond to different continuous limits. So the continuous limit of these things would be a more general action, which will involve higher powers of this normalized curvature times these things. So it will be some kind of. So there is some relation between lambdas and t's, which I will not explain now. Remarkably, so this way, in a sense, you have an infinite series of generalizations because you can use all possible Casimirs. For a given gauge group, there will be nonlinear relations between them because you only have n dependent Casimirs. But what is not obvious from this formalism is that the actual space of deformations is twice as large, and that we can see in the continuous theory, which I will explain. So you see here I was fiddling with this Casimir part, but that part was kept intact. So there is something which has to do with, I would say, reparametrization of the group manifold, which can be packaged into a second set of couplings, which you cannot really guess unless you have some intuition from string theory, and that's sorry, let me not puzzle you with this at the moment. Let me just explain what it is from the topological field theory point of view. Okay, so let me just ask one question. So what we did was we had a kind of a lattice definition of two-dimensional gauge theory, for which had the property that you could add or remove edges, so make the triangulation finer or coarser, and ultimately you can remove all the edges except for those which are really needed for topology. And so if you have a Riemann surface of genus G, you know that you can glue it out of a 4G gone, which probably I failed here one. Okay, so this is A1, this is B1, this is A1 inverse, this is B1 inverse. Okay, so this is so this notation means that I'm supposed to identify this edge with this edge preserving orientations, this edge with this edge preserving orientation. So if you do it carefully, you will see a handle appearing. And so 1, 2, 3, 4. Oh, actually, so this should give you, so these defections will give you genus 2 surface.
So let's say in flat space you would get a square.
So the simplest one would be a 4 quadrangle. So if you identify this side, this side, this side. So this is genus 1. So that's it. That's the torus. For the sphere, you don't. Okay, so we'll discuss how to get sphere at the tutorial. But the formula. So the formula is in the end simply that the partition function on the Riemann surface of genus G and area A is the sum over all reducible representations of the group. Dimension of the representation to the power 2 minus 2G. G is the genus, the number of handles, times exponential minus sum of tk, the k Casimir of the representation. So this is with all couplings times the area.
This is the result that was derived first by Bose-Russell problem.
By
Russell.
No.
I think Migdal was the one who got it for as simple as Casimir, and then people understood it soon after that it can be generalized.
Nikita, I have a question. I mean, so the fact that you put it on the lattice, that frees you from gauge fixing and introducing gauss about this story?
Sorry.
Why don't you fix the gauge and introduce ghosts?
Why do you want to?
Okay, we could,
Well, usually it's needed, but maybe only in the lattice system.
well, on the,
Gauge theory, you don't
well,
fix the gauge.
we don't have to fix the gauge if you know how to integrate over the.
In this case, you can actually do the integral, but last gauge theory, fix the gauge.
Well, on the lattice, so that's the result.
This is the lattice.
I know.
This is, however, a lattice that you can make arbitrarily fine.
Okay, so
that's also
the
continuous.
question, whether it's because of the lattice that you don't have to do that.
Yes. So of course, okay. So there was a hidden assumption in what I said. I did not say it explicitly. Thank you. So my assumption was that my higher measure in the group was normalized. It was normalized to be 1, and that's why I didn't fix the gauge explicitly, because the volume of the gauge group, which was 1, irrespectively of the number of vertices. If I didn't do that, then I'd have to be more careful with the factors.
I'm curious, for example, if you would take a large n large genus limit, Would you get some extra structure from?
Sure.
So in the infinite genus limit, do you get something?
Yeah, well,
Because people were curious about what infinite genus can give in various setups. So
I don't think infinite genus.
Genus becomes, in a sense, since it's 1 over dim R.
Yeah, it just supports only a trivial representation. So it
Yeah,
sort of
it
kills
becomes
everything.
trivial.
also, well, I tried to add UNN to get some double scaling limit or something to keep stuff.
Well, you see, okay, so maybe I should say something about this. So,
I think the genus only comes in this dimension, so it doesn't take out the.
right, you see, it's so there's something misunderstood about topological field theories, which is so it looks like it's a very simple formula because it only depends on the genus and the area. And in fact, apart from this thing, which I will interpret later, this is actually a particular case of a universal formula. So in any topological field theory, the partition function on genus G has the form of the trace over some space. So this is the space of primary states. Primaries or physical states or topological states of some operator raised to the power 1 minus G. So this is called the Handel gluing operator. And so this is true for gauge theory with compact gauge group. It would be true for gauge theory with finite group. So for example, if I, instead of the Lie group, I had here a finite group, and if I cross this factor for the moment, this will be a finite sum. It would still make perfect sense as the partition function of a gauge theory based on a finite group. And what this theory counts, it counts some kind of covers of Riemann surface sigma. The structure group is the group G. Now, introduction of these factors actually has a meaning. And so this would be counting covers with additional conditions. Certain branch points, so you fix the types of branchings at some points, and you have generating parameters to account for those. So this is actually a partition function. So this is still, so it's a partition function of a topological field theory perturbed by so-called zero observables. Yes?
Can you repeat what's the
So these are higher Casimirs.
Okay.
So
These are just coefficients.
and TKs are parameters. So the parameters of the theory. Yes, the coefficients which you first you fix at each plaquette. They
They're not variables, but they're parameters.
they are parameters of the theory. We could imagine actually having these parameters different at different plaquettes. At each plaquette would have different parameters. But in the end, because of this additivity property, the final answer depends only on sum or on the sum. So instead of writing TK times the area, I could have written the sum over all plaquettes of TK for that plaquette. So it will be, if I kept all TKs here of all plaquettes, it would be huge redundancy. So this whole thing depends only on this.
Each plaquette is a different.
So imagine that on each plaquette I turn on all Casimirs with different fugacities. So this chemical potentials. These would be like chemical potentials. For local plaquette I have local chemical potentials, but the partition function does not depend on this individual chemical potentials. It only depends on the sum. So like an integral of them.
Then it's not really the area.
So the area is slightly misleading. Actually, area is slightly misleading term. So, and this is what I'm trying to say. So so let me explain this in the language of continuous, continuum theory. So this theory is best described in the first order formalism. So first. So let me write as an action integral of sigma trace phi f plus first let's carry determinants first. Just trace phi f minus plus tk trace phi to the k, so the sigma, and so in order for this to make sense, so phi is a scalar field, phi is an adjoint valued scalar, f is a curvature of my continuum gauge field, continuous gauge field, and so here I'm just taking all possible gauge invariant functions of phi, which I denote schematically as trace phi to the k, and I want to smear them over the Riemann surface. So I would put here omega because I need the two form to integrate the surface, but really omega times tk is just another two form. So it's a matter of notation. So in what sense? So I said it's smearing. In what sense it's smearing? Suppose that I didn't have this term. So let's treat this term as perturbation. Then the equations of motion. So let's call this term as 0. Will tell me that the covariant derivative of phi is equal to 0. So it means that if I have an observable trace phi to the k inserted at some point x, and I want to move it to some point y, so this is the integral over some path connecting these 2 points. Trace the covariant derivative of phi times phi k minus 1. And this is equal to 0 under the correlator, assuming there is no such term. So this is equal to 0 modulo equations of motion, or under the correlator. So it means that this observable, the zero observable means that it's a scalar on the wall sheet. This is 0. It is truly topological. I can move the insertion point and its expectation value doesn't change. Now, what I do here when I add this term, I'm adding this observable to the action, but I can add it in many ways. I can integrate it, add it as an integrated observable, or I can just take it at some point and add it. The effect will be the same. So this is to be contrasted with true deformations of topological field theories, which has to do with the so-called two observables. And so I need to introduce a little bit of supersymmetry to explain what they are. So the
if you would add just phi squared, you would get back the QC.
So yes, if you integrate phi, if you add phi squared, and if you integrate phi out,
F squared.
you get usually Young-Mills theory. So if you add kind of a bunch of these couplings and integrate phi out, you will get the generic action of this form. So then T will be related to lambda through extremization of a generic function. So then there is some. But what I'm trying to say is that there are other deformations of this theory. And so the other deformations, they change the phase space structure. They change the nature of the conjugate momentum, momentum conjugate to A. And, so other deformations the term trace F deforms to sum over k subcoupling S sub k trace phi to the k. So, so it looks like, so it is allowed by gauge invariance, of course, and by all dimensional considerations, because phi is a scalar. But what is it really? Really, I'm trying to reparameterize the phi variable. I'm trying to do a kind of a field definition when phi goes to some generic function of phi. And that will screw up the measure. So my original measure was d phi dA, and of course it doesn't like such a parameterization. So what happens is that you have to introduce fermions, which
What does it keep the measure?
say it again.
Jacobi.
What's the problem with the measure?
So if I just make this definition, phi goes to the generic function of phi. So phi goes to well, then this measure will pick up some non-trivial, some Jacobian, which naively you would have to recalculate, and maybe if it's local, if it can be written as a local exponential local functional, it will shift the variables t. But the proper way of doing this is actually to embed it into a structure which guarantees that you preserve topological invariance, and that structure is supersymmetry or cohomological symmetry. So this
again, so you could add a term where F does not couple to phi. Do you add also this term? You call TK.
You mean k equals to 0? Yes, you could add it. K,
I mean, it's the first line here. So
K
you
equals
add
to 0.
both in principle?
yes, you have both. Yes.
Okay.
In fact,
But you're worried only about the one with where phi couples to F.
yes. So these are the true deformations of the theory. They really deforming. They deform your topological field theory into a different type of topological field theory. So just to so I know Igor was supposed to talk about Landau-Ginzburg theories. Igor Kleban. So there is a supersymmetric version of Landau-Ginzburg theory, which people might be familiar with. So these deformations have to they're the analogs of deformations of superpotential. These deformations are slightly less familiar because this is called in the language of supersymmetric gauge theories in 2 dimensions. This corresponds to turning on a non-trivial twisted superpotential. So the conventional Yang-Mills theory corresponds to the quadratic superpotential trace phi squared, and turning on this additional times makes it generic. And you may have a critical behavior, as you know, when you get a superpotential with degenerate critical points. So for the time being, if I treat these parameters as small, I will get a small perturbation of my theory. Nothing will change drastically. It will have the same features, although they, I mean, there might be something happening at finite values of these couplings. So you could get some caustics, but the truly interesting behavior happens when you fine-tune the parameters when, for example, phi disappears and the leading term will be trace phi squared f. So then you get a different universality class of a gauge theory in 2 dimensions, which has not been explored.
What does it look like over here?
I don't know. That I don't really know. It's so the point is that for so I know what it so I for these deformations when S is small, I can tell you what it is. In this case, it can be reabsorbed. It can be absorbed in the redefinitions of T. So this program of calculating the Jacobian and doing all that can be done, and it just becomes a redefinition of T. But that works assuming that a certain matrix is invertible. And it's a metric. Basically, it assumes that this is a field definition. Map from phi to phi hat is one-to-one. Once it becomes singular, once you get, then it's a new critical behavior. And so then it has not been explored. It has not been explored. It's like the, so I believe there are other kinds of minimal models which are hidden here. So the minimal models which Igor was supposed to talk about, they correspond to Landau-Ginzburg theories with ordinary superpotential, which in the language of n equals 2 supersymmetry, these are chiral fields with superpotential. And gauge theory corresponds to twisted chiral fields with twisted superpotential. And there are certain subtleties which make them differ. All right. So the message which I wanted to make was the following, to convey, was that, at least this part. So there is this.
So these are. So we can use this first order combination determinants to prove localization.
Right. Localization
That
works for all
works
these
here,
deformations.
all
All these deformations. Yes. No, in fact, he found this way of kind of dealing with this higher order, these deformations by the streak, but it only works for formal parameters S. So it means that in the modern language, he didn't know about, I mean, he didn't know this relation. So in modern language, he was working in the vicinity of the quadratic superpotential, and that's the simplest type of singularity. It's the Morse type singularity, which doesn't have non-trivial primary fields. So things start at phi cube, and that's
As you mentioned, Witten, is the operator H the one he called W in his paper of topological sigma model? The H in the...
no, I think it's always called H,
It's
because it's a handle
Handel-Lewis-
gluing operator. It's
I
a
think
handle
we
gluing.
called it W, I think. If you remember Shmuel.
So in the general,
It allows you to go from genus to genus.
right, but it's cheating. Okay, so there, it has a universal expression, that's for sure. So if you have the two-dimensional topological field theory, it has this structure of the product of primary fields, which can be obtained from the three-point function in the sphere, and this handle gluing operator is something like so it's eta ij. So eta is the topological metric. It's an inverse topological metric.
We called it W.
The star is this the dot product. But what I want to say is that nowadays we think of the topological field theory as a kind of a package which lives over the modular space of Riemann surfaces. So it means that in addition to all these deformations, in addition to so these are zero observables which are interesting for some purposes, but it's kind of simple. You can actually couple the theory to topological gravity. You can actually couple to two-dimensional gravity in a serious way. Namely, you introduce the metric. So, for example, what Kobe was asking me about, like gauge fixing. Gauge fixing depends on the metric, typically. And you can actually try to see if you make some big change in the metric. So you go in a space of metrics modular diffeomorphisms around some loop, or maybe go around, find a cycle in that space, and it has very huge topology. Then there is some trace of that topology in the correlation functions of this theory. But you have to go deeper. You have to introduce additional observables which are normally not considered in this naive setup. So these observables which require stress energy tensor, and that's okay. But it's a separate story. So the reason why I wanted to start with two-dimensional angles was that in this context, it's easy to understand the need for codimension to defects. So that's why this is, you get that when you start thinking about the factorization properties. So suppose that I took my Riemann surface and started pulling out long necks. So my Riemann surface has this form which is mathematically called the connected sum of two remote surfaces. So we had surface sigma 1, I dug a little hole here, and surface sigma 2, dug a little hole here, and glue the cylinder connecting them. Then, in general quantum field theory, you expect the partition function on this union long neck to split as the sum over intermediate states. And then these would be partition functions on sigma 1 with insertion, so it will not be a partition function. So the operator which represent the state in the state operator correspondence. And kind of dual operator in the theory limit surface sigma 2. So this is the usual factorization. Now, what would it mean in the context of gauge theory? Well, in gauge theory, my variables are gauge fields. So if I cut it along the cylinder, what I see, so I see a circle. But now on this circle, I have the gauge field. So the partition function on sigma 1 with this little hole will depend on the holonomy around this point. And so it's different, it's a slightly different calculation from the one which we just did. We should take into account the fact that I have a holonomy. Or in the Lattice formulation, so if I had a little plaquette, so okay, I could have done this factorization at the level of triangulator theories. As long as I can identify the plaquette which comes from the left to the plaquette which comes from the right. But since I want to identify them, I don't want to integrate out the degrees of freedom which live on these edges before I glue them together. So it means that for various purposes, it's useful to have, as a bookkeeping device, the information about the partition functional theory where on one plaquette, I fix the holonomy. Actually, because of gauge invariance, I don't fix the holonomy, I fix the conjugacy class of the holonomy. And so it means that now, because of the considerations we had, the size doesn't really matter, the area matters. This can be made I can make this plaquette of very small area, but still keep the holonomy non-trivial. So, to make the long story short, this will become a codimension 2 defect, which is labeled by the conjugacy class of the group of the holonomy. So G is the conjugacy class of the holonomy of a gauge field around the small loop. So this is so since it only depends on the conjugacy class, then of course we expect the answer to be able to expand it in characters again. And so let me just write it here. Sigma 1 with the insertion of one defect. Corresponding to G, it will be just means that replacing this factor 2 minus 2G by 1 minus 2G and inserting the character of G in that representation. Now, I will leave it as an exercise, so maybe we'll go over that in the tutorial. If I have tons of defects, defect 1, defect 2, defect K, so they all correspond to their own conjugacy classes. Each of them, so inserting them just means removing one more dimension and replacing it by the character. So this is still the same sum, and then so just the product character in the presentation R of the conjugacy class GI divided by dimension times dimension to the power 2 minus 2g times the same area TT. Now, in the continuum theory, so you can ask, what is this operator? How does it look? What does it look like in the continuous theory, and what does it imply for the equations of motion of Yang-Mills theory? This is called a Wilson point operator. Okay, so it's a continuous version of defect. So it will be so I will label it not by the conjugacy class in the group, but by the conjugacy class in the Lie algebra. So it will be in the Lie algebra modular the adjoint action of the group. And what this element is, what this observable is, it's an integral of the group itself, exponential I trace. So this is at some point x is on the surface. Phi of x, g inverse lambda g. So this is called, sometimes it's called Harishchandra-Itzikson-Zubair integral. And it's so its meaning it's a kind of a quasi-classical limit of the normalized character in the representation. So think of it as a character in the representation R, which would be the quantum eigenvalue of phi. So the highest weighted representation R is the eigenvalue of phi, evaluated on the exponential of lambda. So, in doing path integral, we're localized. So there's a kind of localization on the values of phi, for which the trace of phi to the k becomes the kth Casimir of the representation R. And so, in some sense, the character of R can be expressed in terms of the Casimirs of R, and so you can, in some sense, you can re-express it in terms of the Casimirs of phi. So we know for SUN, for example, this can be evaluated explicitly. So some kind of ratio of determinant of exponential eigenvalues of phi, eigenvalues of lambda, divided by Vandre mode of phi and lambda. And so this is a symmetric function of the eigenvalues of phi. Therefore, it can be expanded in the Casimirs. But it's a complicated function of Casimirs. So now, what's nice about this representation of this function? It tells us that again, in the absence of this area term, the path integral compute the path integral over A and over phi with these operators. So this is a point x1, this is a point xk. So this is the zero area limit, which gives us first hint. So So if I integrate phi out, I will get the delta function. So my curvature will now become sum of the delta functions, lambda I, gi inverse gi, delta function of xi. So, so in the presence of these observables, the leading contribution to the path integral comes from the connections which are flat everywhere except at these points, and the holonomy around, so the holonomy around the small circle around point xi is conjugate in the group to the exponential of 2 pi I lambda. Right. So so on one hand, so you can compute, for example, the volume of the modular space of flat connections with punctures using this formula, and actually it's a remarkably interesting formula because it tells you that the function which you expect to be periodic in lambda, periodic in so it should depend only on the conjugacy classes of holonomy, not on the eigenvalues of lambda themselves. But this formula expresses it actually as a polynomial in lambda, and so it's an interesting type of formulas where you get these Bernoulli polynomials, which are polynomials on an interval which can be periodically extended. So they are locally polynomials as summations. So it has to. So these sums have to do. There is a lot of zeta function. There is a lot of number theory. There is a lot of interesting story. Only even z is low. So to get to big bucks, which mathematicians are interested in, odd zeta function, odd values of zeta function, you need to go up in dimensions in gauge theory. So we spend our time today in 2 dimensions where only simple things show up. But they show up in an interesting way. Now, this argument that you need these defects for factorization now can be lifted to higher dimensions. And so that motivates that in high-dimensional topological field theories, and therefore in any field theories, if you want to allow all kinds of factorizations when your intermediate channel is a manifold of the form, for example, a circle times something 2-dimensional in deformation theory, that would imply that the half of the space-time which you will get by factorization will contain this codimension 2 defect, which will be a surface defect. And so that motivates the study of such defects in 4-dimensional gauge theory. So this plaquette definition carries over to 4 dimensions. You can define it in this way. But to make it something which can be computed and controlled requires a certain amount of supersymmetry. And so I have 5 minutes left. Let me just state a result, which I think is remarkable. And if you don't believe in extra dimensions, when you look at the mathematics of these formulas, you're forced to at least admit them, at least in the Platonic sense, that at least in some ideal world of ideas, the high-dimensional theories should exist. Anyway, so the result about the 4-dimensional super-anneals theory with n equals 2 supersymmetry. So we have vector multiplets and hypermultiplets. So gauge fields live in vector multiplets and quarks live in hypermultiplets. So so the simplest theory would be super QCD. Super QCD, where you have so you have NF hypermultiplets and C vector multiplets And if NF is equal to NC, this is a theory with vanishing beta function to all orders. So it's a superconformal field theory. But to make it interesting, I will I will give masses to my quarks. So I will break superconformal invariance, but I will break it in a kind of a soft way by just giving masses. Now, so in the ultraviolet, the theory, the masses are negligible, so the theory is exactly superconformal, and it is characterized by the gauge coupling, which is a true parameter, and the theta angle. 5 minutes or
3 minutes.
3 minutes, yes, yes. I'll be very fast. So there is so these are parameters of the theory, and there's also a parameter of the vacuum. So this is the theory, and the vacuum expectation of the scalar in the vector multiplet vector. It's a diagonal matrix with n eigenvalues. So this is a choice of the vacuum. And now I do two things. So we didn't discuss it much, but we did discuss studying field theories in various space-times with various metrics. So it's an example of a background. So you can if you have a theory with some symmetries, you can turn on background gauge fields for those symmetries. So if you have a theory with Poincare symmetry, the corresponding gauge field will be space-time metric. But these are not the only possible examples. And if you have theories with like this one, when, for example, vector multiplet, the gauge field come with it has a superpartner scalar. In some sense, this theory actually comes by reduction from a high-dimensional theory. And so you can turn on the background where the metric in the high-dimensional space is curved. And so there is a deformation of the theory which takes advantage of this fact and has two more parameters, epsilon 1 and epsilon 2. So these are omega deformation. So this is a deformation of the theory. So this is theory, this is vacuum. These parameters have dimension of mass also. They have a meaning of angular velocity in two orthogonal planes of a four-dimensional spacetime. So it's like when you study rotating black holes, so this is like rotating, subjecting the theory in rotating black hole. Okay, so now I want to do something with this theory. It has, so I like two-dimensional Yang-Mills theory, which was mostly about flat connections and maybe constant curvature gauge fields, to which it exactly localized. So this theory localizes on instantons. The instantons come in all sizes and shapes. It's a whole story of how to integrate over them. It has been done. There is some combinatorics about it. And now we can study these effects for low energy, what's the effect on low energy effective theory, but also on the behavior of various defects. And so one defect which I want to insert is a two-dimensional defect. So this is my four-dimensional space-time. I will describe it as a complex plane with coordinates z1 and z2. And so I will place the defect at z2 equals to 0. So these omega deformation parameters, they have to do with rotations. One rotation with parameter epsilon 2 will be in transverse space, and another rotation with parameter epsilon 1 along the defect. So as I briefly mentioned yesterday, the defect supports a two-dimensional sigma model. So there is a sigma model. So okay, in this example, the defect supported zero-dimensional sigma model valued in the flag variety in the G mod T space. So this observable O of X was really the integral over G mod T. So this was this integral. So the point X was mapped to this space. Now I have this whole surface. So this whole surface is mapped to this Lag variety. And so there are additional parameters, which are the theta angles. And there are n of them up to the whole translation. So x1. And so the partition function of this defect, so it's a function of x1, xn, it depends on the choice of the vacuum of the original theory. It depends on all the parameters of the original theory. So it's something. It's some function of all these variables. And the bottom, the punchline, it's a solution to Knižnik Zamolodchikov equation for a two-dimensional theory which has an SLN current algebra with 4 vertex operators sitting in 4 points on a two-dimensional sphere, and the points are 0, q, 1 infinity, where q is exponential 2 pi I tau. Tau was this gauge. The vertex operators, I don't have time to explain the parameters, but they have to do with these masses and epsilons. And the level, and that's the most important point, that the level of the current algebra is the ratio, sorry, n plus level, is the ratio of the omega information parameters. So, just to finish. So, mathematicians have studied Knižnik's logical equation. So, Knižnik's logical equation first arose in the context of WCW theory in 2 dimensions, where it is an equation which is obeyed by conformal blocks, which are holomorphic functions of the points where the vertex operators live, and so on and so forth. But the equations, mathematicians observed, the equations admit analytic continuation in all the parameters. Like in WCW theory, vertex operators depend on spin, and there is a level, and level should be an integer, spins should be within certain range. But mathematicians observed that spins can be complex, level can be complex, the equations make sense. The solutions become infinitely more complicated, but they exist. So they were an answer to something, but there was no understanding what was the question. So the question is that it's the solution of, so they describe not the two-dimensional conformal blocks, but the topological defects in the four-dimensional theory. Yet they are holomorphic in all these parameters. So if you take these things together, you have an object which is a hybrid. It's topological in 4 dimensions, in holomorphic in 2 dimensions. But altogether, but you need 6 dimensions to fit all these dimensions, because they're not compatible. And so it's one of the many projections we have of this mysterious 6-dimensional quantum pure theory, which exists but has no definition. And with this, I stop.
Say that question will come in the tutorial in the Think Again